Hello friends, in this particular segment we are going to discuss about the fluorocarbons, polyxylenes and polyesters under the edges of polymer process engineering. Now in the previous lecture we covered about the various aspects of polyamides. We had a definition of these polyamides, then discussed about the structure, physicochemical properties, applications in electronics. We described the various synthetic aspects of these polyamides and different type of the polyamides like solvent soluble polyamides. Then we discussed about the two-step curing process and modification streams of these polyamides. And then lastly we described that what are those photosensitive polyamides and what are their applications. In this particular segments, we are going to discuss the fluorocarbons. We will discuss about the definition of these fluorocarbons, then we will describe the different type of fluorocarbons and the properties. Apart from this, we are going to discuss about the polyxylenes and then definitions, types and different type of properties and synthesis and applications we are going to discuss. Then we will discuss about the polyesters and all aspects of polyesters like definition, different type of the polyesters and applications we are going to discuss. So, let us start with the fluorocarbons. Now, the fluorocarbon coatings, they are the type of a surface coating that contains the fluorine atoms and provide the unique properties like low surface energy, chemical resistance and a non-stick characteristics. And the best example is PTFE, that is polytetrafluoroethylene coating. And all of you are aware about the Teflon coating of the utensils, and they are very much popular nowadays. And this is, they are coated with the polytetrafluoroethylenes, PTFE coating. So, this is a very common type of fluorocarbon coating, and it is known for the excellent non-stick properties. The example is Teflon, Fluon, Xylene, all these things. So, this is the basic structure of tetrafluoroethylene, and then free radical vinyl polymerization, this gives the PTFE or polytetrafluoroethylene. Then the fluorinated ethylene and propylene, that is FEP coating. Now, this FEP is a fluorocarbon resin that provides a good chemical resistance and non-stick properties. Again, example, the Teflon FEP and Dyneon FEP. Now, here this is the basic structure that the tetrafluoroethylene, this is TFE, reacts with the hexafluoropropylene HFP. Under the polymerization condition, it gives this FEP, that is fluorinated ethylene propylene. Another one is the perfluoroalkoxy coating, that is sometimes referred as PFA. This PFA is a type of fluoropolymer coating with excellent chemical resistance and high temperature stability. Again, the example is Teflon PFA and Dyneon PFA, and this is the basic structure of this one. And you can see this type of a film or this type of the things in different buildings, and they are Teflon PFA or Dyneon PFA. Then ETFE, that is ethylene tetrafluoroethylene coating. This ETFE is a fluorocarbon polymer known for this excellent weatherability, transparency and corrosion resistance. Again, the example is Fluon ETFE or Tefzel. So, whenever you require the lightweight covering or sometimes you require the transparent roofing, the ETFA is the better candidate. Now, then I talk about the fluorinated acrylic coating. This fluorinated acrylic coating combines the properties of acrylic resin with the low surface energy of fluoropolymer. Now, example is Lumiflon, and they possess the low surface energy. They are offering the good thermal stability. Apart from this, the excellent chemical and weather resistance and low refractive index and high transmittance. Then vinylidene fluoride, this PVDF coating. The vinylidene fluoride PVDF is a fluoropolymer coating. This is known for excellent chemical resistance and UV stability. Now, the example is kynar and hylar. And there are different type of structure of a different phases of PVDF, like alpha phase, you can see like this, and then there is a structure difference. Here the hydrogen, fluorine and carbon atoms, then beta phase and the gamma phase. Now, there is a comparative study among the FEP, PTFE and PFA. The fluorinated ethylene propylene, that is FEP, they share some of the same non-stick qualities like Teflon, through its structure is slightly different. Now, FEP is softer, therefore it melts at a lower temperature than PTFE. This means that it is less commonly used for cooking and baking purpose, because there you need some elevated temperature, maybe around say 200 degrees Celsius. Now, this FEP, that is the fluorinated ethylene propylene, is highly transparent. So, whatever you see FEP to cover, the object will remain with the same color. So, that is the transparency play a very vital role, and the operating temperature is somewhere minus 200 degrees Celsius to 200 degrees Celsius. They are biocompatible and total resistance to the chemical and ultraviolet light, and they are very much clear in color. Now, PTFA is non-sticky. Despite Jacob's sphere's climbing abilities, Teflon is the only surface to which these creatures cannot stick. PTFE has a high electronegativity, and Teflon, that is a PTFE, the Teflon has been used to coat the bullet cases. Teflon is also used to coat the pharmaceutical needle to make the process less painful and invasive. Now, NASA is looking into the non-stick technology to add their mission to Mars. They are highly chemical resistant, and they can work up to the temperature of say 260 degrees Celsius, and they are translucent in color. The PFA. The PFA is a polymer with the ability to melt processed. It is the high temperature version of FEP with the similar properties, and its structural difference results in improved flow, thermal stability and creep resistance. The continuous working temperature of around 260 degrees Celsius, that is highest among all the fluoroplastics. Now, this PFA is not temperature sensitive, hence it can be used to both high and low temperature environments. And this resists the stress cracking and attacked by almost all chemicals and solvents. They have PFA has a good permeability resistance. It is biocompatible. It is more expensive than PTFE and FEP. So, because of their properties, these fluorocarbon coatings, they have found many uses in the electronics and electrical industries, as a capacitor layer insulation, coating for glass fabrics, and yarns for electrical insulation of motors, generators, transformers, and the wire enamel for magnet wire insulation, and as a low friction corrosion protective surface coating. Let us talk about the electrical properties. Now, these fluorocarbon also exhibit one of the lowest dielectric power losses over the same temperature and frequency ranges. Now, dissipation factor, this ranges from 0.001 to 0.001 as per in this table which is shown. Now, with the Teflon TFE having somewhat lower values than Teflon FEP, which you can see that in here we have enlisted the dielectric constant and dissipation factor for Teflon FEP as per the ASTM standard 150692, and the temperature ranges from 73 Fahrenheit to 100 Fahrenheit. Here the different type of frequencies enlisted, and then their dissipation factor and dielectric constants. Now, surface and volume resistivities are very high for both TFE and FEP. Now, surface resistivity measured according to the ASTM D257-52T is greater than 10 ohms, and volume resistivity according to the same procedure is greater than ohm centimeter. In both cases, there is a little variation over the temperature ranges range from -40 to 230 degrees Celsius. The dielectric strength values are also very high, and it is given in this particular table from film thickness from 1 to 100 mils, that is from in volt per mils. This is the dielectric strength of Teflon FEP as per the ASTM standard for the short time test. Let us talk about the mechanical properties. The two outstanding properties of Teflon are their low coefficients of friction and the lowest for any known plastic material, and their high abrasion resistance. Some of the experimental values of these properties are given in this particular table, and the frictional properties of Teflon are so good. In fact, you see that they are often used as a filler in other plastics like epoxies and acetyls to lower the coefficient of friction and improvise the wear properties. Now, here you see that the constant coefficient of friction of Teflon against the steel at 23 degrees Celsius. Now, here you see the abrasion resistance of Teflon TFE and FEP coating, that is Armstrong 20 cycle test as per the ASTM standard, then Tabor test. So, all these things you can clearly distinguish, and you can have a look about the weight loss of FEP and TFE. Let us talk about the chemical and solvent resistance. Now, these fluorocarbon polymers, they exhibits exceptional resistance to a broad range of organic and inorganic acid, bases, solvent and gases, make them highly effective in corrosion protection for metals. Now, they demonstrate outstanding chemical stability with the exception of exposure to the molten alkali metals like sodium, potassium, free fluorine gas, and fluorine precursors like oxygen difluoride and chlorine trifluoride at elevated temperature. Now, even in cases where there may be slight absorption of chemicals and weight increases, fluorocarbon retain their physical and electrical properties remarkably well without significant deterioration. Now, their resistance to aggressive substance contributes to their suitability in demanding environment where corrosion protection and durability are critical. The fluorocarbon polymer, they offer a reliable solution for applications that involve exposure to harsh chemical environment, ensuring long lasting performance and maintaining the integrity of the protected material. Because sometimes you need to expose the very rigorous conditions like concentrated acid or sometimes extreme heat or humid environment. So, all these things, the resistivity towards all these things must be addressed when we are using such kind of the polymers. Now, here you see that the chemical compatibility of a TFE and FEP resins we have discussed, like with different chemicals and their resistance in degrees Celsius, like abatic acid, acetic acid, acetone, acetophenone, aniline, benzyl alcohol, all these things we are listed, and you see that dibutyl phthalates and dibutyl phthalates, all these things. So, you see that they offer the resistance to a very high degree temperature. Similarly, if you see different type of things that the TFE, oil and animal vegetables, and FEP, then again they offer a high degree, high temperature resistivity. Similarly, if you see that different type of chemicals being compatible with the TFE and FEP resins, so you see that why here we are using this TFE, PTFE, because you need see, if you go for deep fat frying, etc., you need to have a temperature around 200 degrees Celsius. So, they are resistant to up to the temperature range of 260 degrees Celsius. So, you can use these things very easily. But if you are using, say, other things like cetane and other carbon disulfide, they may not offer such kind of thermal resistivity. Again, some of the exposure of Teflon resin to the common acid and bases. Again, the exposure temperature, you see that they are very much higher to the hydrochloric acid, nitric acid, and the exposure time and a weight percent increase. So all these things offer a good candidacy towards the specific application of these FEP. Then let us talk about polyxylylenes. The polyxylylenes, they are the family of polymers that are characterized by a repeating unit of paraxylene. The most common polyxylylene polymer is polyparaxylene and also known as Parylene, which is the high performance polymer with a range of unique properties. This is the structure of polyxylylene, and here different type of the Parylenes been enlisted. Now this Parylene is a unique polymer that is deposited onto the surface of a gas, which then polymerized to form a thin conformal coating. This coating has several unique properties like excellent barrier properties. This Parylene has excellent barrier properties, making it ideal for use as a protective coating in a range of applications. Then biocompatibility. The Parylene is biocompatible, meaning it is not harmful to the living tissue and has been used in a range of medical application. Then chemical resistance. This Parylene is highly resistant to chemicals and solvent, making it ideal for use in harsh environment. Then high dielectric strength. This Parylene has a high dielectric strength, making it an excellent insulator in electrical applications. Then the low water absorption. The Parylene has a very low water absorption rate, making it ideal for the use in the application where the moisture resistance is extremely important, especially in case of electronics. Then high purity. The Parylene is highly pure and does not contain any additive or impurities, making it ideal for use in sensitive applications like electronics and medical devices. Now, that is also used in the range of applications including the protective coating for electronics, medical devices, aerospace components, as well as the micro electromechanical systems, MEMS, and other advanced technologies. Now, let us talk about this polyxylylene synthesis. They are prepared by pyrolytic dehydrogenation of gaseous paraxylene. Now, at temperatures of say 700 to 1100 degrees Celsius and reduced pressure of say 1 to 5 torr, the paraxylene loses a molecule of hydrogen and converts into an unstable quinoid structure. So, upon quenching, this particular structure polymerizes rapidly to the desired polyparaxylene. Now, here this is the paraxylene, and this is once this is dehydrogenated. So, it converts into the quinoid structure, which in situ polymerization gives the polyparaxylylene. Now, two key members of the Parylene series are Parylene N and Parylene C. This latter is structurally similar to the Parylene C, except that one chlorine atom is contained in each benzene ring. Now, here you see the difference between these two. This is the Parylene N and this is the Parylene C. So, this the chlorine in the benzene ring differentiates between these two things, Parylene N and Parylene C. Now, in addition to Parylenes N and C, more than 40 other derivatives have been synthesized. Now, some of the things been reported here. This is the coating. This coating is anti-corrosive, biocompatible, then antibacterial, therapeutic, and all those things being used. Now, here you see that different type of thing, masking pattern, and then oxygen plasma penetration, all these things are given, like resistance, then this Parylene C film with the silicon substrate, then etching and all those things there. Now, this is widely adopted as a conformal coating for protecting printed circuit boards, PCBs, and particularly for intricate boards with a high component density. Now, compared to the spray type coating, vapor deposited Parylene offers a notable advantage by effectively penetrating and coating areas beneath and around closely spaced electronic components. Now, here you see that different conformal coating like sublimation, pyrolysis, deposition, then it is subjected to the pump and cold trap. So, the sublimation is carried out in vaporizer, and then the pyrolysis in the pyrolysis furnace, and this is your coating chamber where you can deposit the things, and then the vacuum pump removes all air and the gases from the chamber, enabling the Parylene deposition. So, the metallographic examination, when we talk about the electronic application, so the metallographic examination, this confirms that the Parylene uniformly coats space to narrow as 2 mils between wires and components and the substrate board. The ability of Parylene to uniformly coat these tight spaces is crucial, preventing the entrapment of contaminants that can lead to the corrosion and a deterioration of these electrical appliances or electronic appliances with respect to the electrical properties. Now, the Parylene coating exhibits favorable electrical properties, this including high initial electrical insulation resistance and minimal degradation even after exposure to humidity and temperature cycling. Now, here you see that the Parylene C circuit board screening test as per the MIL standards 202 method 302. Here the initial measurement, then pre-cycles and different type of steps being carried out. Now, in hybrid micro circuits, Parylene is used as both protective coating for moisture resistance and as a coating to immobilize loose particles and small fragments of conductive material. This can cause the electrical shorts if they bridge wire bound or conductor lines. Now, these very fine particles are difficult to remove by conventional cleaning because of their strong electrostatic attraction to the circuit. Now, a thin coating of Parylene, say 0.1 to 0.25 mils, will immobilize particles, preventing future electrical failures. Another interesting application of Parylene is as an insulation and a barrier coating applied over inorganic passivation layer of semiconductor devices or over thin film circuits. Now, Parylene coating as thin as 3 to 7 micron have been deposited on metal oxide semiconductor transistor, diodes, resistors and capacitors. So, after being coated, these devices were subjected to the variety of stresses, including temperature stress of say 125 to 175 degrees Celsius for a period up to say 128 hours and a voltage stresses of say 10 to 20 volts. The changes in electrical parameters such as threshold voltage and a leakage current, they are negligible in most devices, and the average threshold voltage shifted less than I see 0.1 volt, and the breakdown voltage changes less than 1 volt, and the leakage current drifted within a few picoampere for all groups. Let us talk about the polyesters. Now, they are unsaturated polyesters. They are significant class of thermoset molding resins, and they are produced by condensing a diol with a blend of saturated and unsaturated anhydrides. The reactive resins, they are formed through this condensation process, which can create the durable structure and coating. And the properties of the cross-linked resin depend on the types and amount of anhydride and glycols used. Phthalic and maleic anhydride along with 1,2-propylene glycol, they are commonly used component in commercial unsaturated polyesters and sometimes referred as UPR. And other glycols and acids or anhydrides, this can be utilized to modify the properties of unsaturated polyesters. Isophthalic acid IPA and terphthalic acid Ta. These enhance the thermal and chemical resistance, while long chain aliphatic acid improve flexibility but reduce the chemical and heat resistance. Now, ether glycols like diethylene glycol and polypropylene glycol can increase the flexibility. The monofunctional acids and bases are used to control the hydroxyl and carboxyl group and reduce the molecular weight. Anhydrides and acids can be condensed with epoxy resin, and carboxylated unsaturated polyester can be captured with glycidyl methacrylates, and these resins find application in ultraviolet curable coating formulations. Now, here you see the typical example of maleic anhydride with the phthalic anhydride and the propylene glycol. This gives different type of things, and then cured polyester can be formed like this. Let us talk about the curing mechanism. The curing mechanism of unsaturated polyester involves a cross-linking reaction between the polyesterification, which is known as a polyesterification, where the unsaturated polyester resin reacts with the cross-linking agent or initiator to form three-dimensional network structure. So, the first step in this case is the initiation. The curing process begins with the initiation step, where a free radical initiator generates the free radical, and then a common initiator used in the polyester curing includes the organic peroxide or azo compounds. The example initiators are benzoyl peroxide, methyl ethyl ketone peroxide, dicumyl peroxide. All these are the initiators. Then propagation. The generated free radicals react with the unsaturated sites, and usually they are double or triple bonds, and they present in the unsaturated polyester resins. Now, this reaction is known as propagation, and it leads to the growth of the polymer chain through the addition of different monomers. The unsaturated polyester resin, this contains the reactive sites and typically maleic or fumaric acid functionalities, which can undergo the addition reaction with the free radicals. So, as a result, the polymer chain continue to grow, leading to the formation of cross-linked network. Now, next step is the cross-linking. As the polymer chain grows, they begin to intertwine to form the cross-linking, and cross-linking occurs when the growing polymer chain reacts with each other, creating the three-dimensional network, and this network structure gives the cured polymer resin its mechanical strength, dimensional stability, and other properties which required for that particular polymer. Let us talk about the curing conditions. The curing process is typically carried out at elevated temperatures to accelerate the reaction rate. The temperature and time required to complete the curing, this depends on the specific resin formulation, what you require, and the desired properties of the final product. For example, a common curing temperature for unsaturated polyester resin is around 60 to 80 degrees Celsius, and the curing time can range from several minutes to several hours. Now, catalysts and accelerators are often added to the formulation to speed up the curing process or enhance the properties of the cured polyester. Like cobalt-based compounds or cobalt octate, this can act as a catalyst to promote the formation of free radicals and accelerate the curing reaction. Some of the examples of polyesters are orthophthalic polyester. This is widely used type of unsaturated polyester resin, and it is typically cured using the organic peroxide as initiator, and the peroxide initiator decompose at elevated temperature, generating the free radicals that initiate the cross-linking resin, and this can be represented by this reaction mechanism. Another is the isophthalic polyester. This type of unsaturated polyester resin offers improved chemical resistance compared to orthophthalic polyester, and the curing mechanism is similar to the orthophthalic polyester. This involves the use of peroxide initiator. Then dicyclopentadiene, DCPD, modified polyester. This is a cyclic diene that is incorporated into the unsaturated polyester resin formulation, and during the curing, this DCPD undergoes a Dieldar reaction, where it reacts with the maleic anhydride groups in the polyester resin, and this reaction leads to the formation of additional cross-linking and enhancing the resin's mechanical properties. Now, this DCPD is a cyclic diene that incorporated into the unsaturated polyester resin formulation. Now, during the curing, this DCPD undergoes a Diels-Alder reaction where it reacts with the maleic anhydride group in the polyester resin, and this reaction leads to the formation of additional cross-linking and enhances the resin's mechanical properties. Now, different types of polyesters are there. They are the class of polymers characterized by the presence of ester functional group in their chemical structure. Three commonly known polyester types, that is polylactic acid PLA, polycarbonates PC, and a polyethylene terephthalate PET. Here are the physicochemical properties and the differences. You can see these are the ester group, then this is the PLA, and this is the PET, and this is the polycarbonate. Now, polylactic acid is a biodegradable polyester derived from the renewable resources such as cornstarch and sugarcane. It exhibits good mechanical properties like high stiffness and strength. It is PLA is transparent and a glossy appearance. It has a relatively low glass transition temperature around 60 to 65 degrees Celsius. PLA is resistant to the common solvent but can degrade under a high temperature and a prolonged exposure to moisture. It finds application in 3D printing, packaging, disposable products, and biomedical applications. Now, let us talk about the polycarbonates. It is a transparent amorphous polyester known for its high impact resistance and excellent dimensional stability. It possesses the good heat resistancy, can withstand at high temperature without deforming. It exhibits a high optical clarity, excellent high transmission, relatively high glass transition temperature possessed by this PC at around 145 to 150 degrees Celsius, having the good insulation properties. That's why it is being used in the automotive component, electrical enclosures, optical lenses, and safety equipments. Then polyethylene terephthalate PET is a strong and stiff polyester, good mechanical properties, excellent dimensional stability, resistance to moisture and a chemical. Now, this PET is transparent, providing the good clarity and a light transmission. It has a relatively high glass transition temperature around 75 to 80 degrees Celsius, and which is widely used in the production of beverage bottles, food packaging, textile fibers, engineering plastics. It can be recycled and one of the most recycled plastic worldwide. So, dear friends, in this particular segment we discussed about the fluorine based polymers, then polyesters, then polyxylylenes, all these things with the synthesis aspect, then various applications, and for your convenience we have enlisted different references which you can utilize as per your need. Thank you very much.